So today we're talking about deep learning for inverse problems and one more application which is not really an inverse problem. But so today we're talking about inverse problems. Until now we discussed how to solve these inverse problems using by inducing priors on X, and some other ways just by searching and filtering, and for in non-local means and things like that. But today we're going to treat this inverse problem as a supervised learning problem, and we'll find a function space which optimally fits both the input and the which translates from the input to the output. And then as we introduce the supervised learning scenario, we'll obviously have to encounter neural networks, because the function that we're trying to that we're using to map inputs and outputs is the neural network, because of its approximation capabilities. And then we'll go into convolutional neural networks. So it's a specific case of neural networks in which the weights are constrained in a particular way. And then we'll talk very briefly about what loss functions to use. We're talking mostly in inverse problem scenario, so when we don't touch classification at all today. So what loss functions to use, and how do you do optimization, backpropagation, and that. And then we'll discuss one or two architectures which are commonly used in the literature. Then we'll see some applications on denoising and CT and MRI reconstruction and deep ISP. It's one of the I'll go into it. And then we'll talk about something more interesting. It's called perceptual losses. So instead of optimizing for pixel-wise loss on the reconstruction, we can rather optimize for something called as a feature-wise loss. And then we'll also define the notion of how do you define style in an image, in a neural network perspective. And then we'll see how we can use these special kind of losses to do super resolution and style transfer. So let us recall what we are studying. So we're studying inverse problems in which y is our measurement, and d is our degradation operator, and x is our original signal. The latent signal that we want to reconstruct. And we have some noise. If d is a focal blur, if d is a focal blur, then it's a convolution operator with some diminishing Gaussian or something like that. Then with the task of recovering is super resolution. If it's motion blur, then it's deblurring. If it's identity, then we're just doing denoising. If it's identity plus some missing values, then it's inpainting. And if it's a random Gaussian matrix, and if we say that X is sparse, then it becomes compressed sensing. So we discussed about it in the last lecture. And if it's a projection matrix, then recovering X is basically doing tomography, and so on. So today we want to approach this problem in a supervised learning scenario. So previously we saw that if X is sparse, then we can. If D is our degradation operator, if X is sparse with respect to some dictionary M, so we can basically represent it like this, and then learn the optimal dictionary, and then reconstruct Y through KSVD. That's what we saw in the last class. And we also saw some other means that we induced some priors that X is a patch. And then we saw that we can find similar patches and create some kind of a discrepancy measure and then filter them. So the closer the patches, the more relevant it is to you, and things like that. And then we saw that we can collect all the similar patches and then apply some kind of a transform on it, and then force it to obey some sparsity. That's what BM3D was. Today we're going to see some different approach to solve this. Just we have Y. It's in a supervised learning scenario. So it is the following: we have Y is equal to dx plus n, and we want to find we want to basically find a parametric inverse model, that is some function which is parameterized by theta, which translates my Y to X, right? And I want to solve this problem by learning over a lot of examples. I give you distributions of all the possible X, and then I want to minimize this L is the loss, which is defined between my reconstructed input and the reconstructed output and the actual one. So by minimizing this loss, I want to find such a theta which basically reconstructs which basically reconstructs X from Y, right? And this is the risk that we define. This is in a machine learning scenario. You can just think of it like your Y's are your regression variables, and you're trying to recover this theta, which is the parameterization of the line, and X is your latent variable, right? So we obviously can't minimize this loss because expectation over all the possible distribution is not possible. So we try to minimize some empirical version of this loss. So we assume that we have m samples, and we want to minimize we want to find parameterization theta, which basically approximates which minimizes this loss. You take a set of examples, and then you want to minimize we want to find such a theta which basically decreases the loss between f theta of yi, which is your reconstructed xi, and the actual xi, right? So if you want to get such a theta, we want it. So let's say it's linear regression. Our model space is very constrained. You will be searching in the space of lines. Or if you extend it to n dimension, then it's planes. Then, or if you constrain it in some other way, let's say if you're doing dictionary learning, it's one specific scenario. You're basically searching in the space of all the sparse codes, and you're constrained by the dictionary D. So you're just searching all the possibilities between all the sparse codes. But we want something that has much better approximation capabilities. For example, that's why we turn to neural networks. It is defined like this. Let's say this is a neural network, fully connected neural network, in which it gets an input y. It just multiplies with some weight matrix W1, and and some bias B1. And basically, the approximation capability comes from this sigma, which is the nonlinearity. So it is shown that neural networks are very good function approximators. For example, if you take a neural network with one hidden layer, but with, of course, infinite width, then it can approximate almost any function. So this is one major motivation that we would want to use such function approximator. But of course, the problem is they have a lot of parameters. It's not very trivial to train them. For example, in linear regression, you have closed form expressions to get what you want. And also in KSVD, you have more or less some definite scenarios. But this is a highly non-convex problem. You don't really have any closed form expressions, or doing second order methods is also not trivial. So basically, if you have a 4-layer neural network, the forward pass looks like this. So basically, you first take your input y and multiply it with a W1, this weight matrix W1, and then you apply B1, and then you take a nonlinearity over it, and then you do the same thing for W2 and B2, W3, B3, and so on. So eventually, the output you end up with is just x hat is defined as the following. So this sigma can be many things. For example, it can be a sigmoid function, or tanh, or ReLU, or all these other functions. Majorly this choice depends upon the problem you're choosing, and also empirically some perform better than others. So most used choice is ReLU or leaky ReLU, but so it totally depends. Let's say since we are working with images, we most probably won't have to deal with negative values. So ReLU could be good. So it doesn't care about negative values. So loss functions, you can since we are considering a regression scenario where you're mapping an image to an image in inverse problem, so you can just define your loss as some L1 discrepancy or L2 discrepancy between the reconstructed x hat and the xi, which is your actual example, and you can minimize this loss for all the data set xi and yi, right? And yeah, and your trainable parameters, the theta that we're talking about before, Our the f theta that we were discussing before are just W1 to W4 and B1 to B4. Okay, so how do we train such a thing? Then basically you just do some chain rule, which is also called backpropagation. So you get the gradient from at every, it's basically a set of matrix multiplications. You get the gradient from the previous matrix, and then you just split it up depending on what weight each one was giving. Just some chain rule, and you can get and basically, since you define a loss on this, and then you propagate the loss for all these W's and V's, and you update them. So how do you optimize it? You just use some very basic gradient descent. So how do you do it? You take a whole data set, you calculate the loss, you backpropagate the loss to update W's and B's, and like this, and you can, but most probably you'll have you'll have to deal with a lot of examples. So you just take a stochastic version of it. You just sample some set of examples which you want to optimize on, and then calculate the gradient with respect to them, and then update the weights, and then do it iteratively until you exhaust the data set, right? So basically the randomness comes from this random sampling of the data set. That's why it's called stochastic gradient descent. And the mini batch is basically defined, it's a jargon used for sampling a subset of your data set, right? So let's see, there was a paper in 2012. What they proposed to do was they wanted to do just image denoising. And they wanted to just brute force it and take patches from, let's say you have noisy images and then clean images. So you take a 16 by 16 patch or something like that from this image, from the noisy image, and then you regress it to basically estimate a smaller patch in the denoised image. So they had fully connected networks, and they basically trained on 362. We saw some nice methods, right? I mean, BM3D and KSVD and all this. So, and then they just brute forced everything, and they had like tons of parameters, like I think 2048 parameters in each layer. And then they just trained on the 360 million patches. Or in clean images, they trained it for a month, and they just and then and that's it. That's all they did. So you see the results. So basically S indicates, I think, a smaller data set, and L indicates a larger data set, and 13 indicates the input patch size, and 17 indicates the input patch size, of course. And this is the size of the network: four hidden layers, 2047 nodes, and that's it. Yeah. They take overlapping patches. They take the whole. They basically swipe through the image through the patch size, and then they put the outputs in the patch. That's it, and overlapping them and averaging. Yeah. So it did not. Yeah, it's. Actually, it's also true for KSVD, for example. Even KSVD operates on patches, right? It replaces the whole patch, and it's kind of known that this averaging kind of produces some additional denoising effect, and also it produces some kind of a lines artifacts between the patches. Yeah. I don't know, but they showed that they showed that in a limited noise scenario, of course, the better the BM3D, KSVD, and all these methods are performing equally well. But as the noise increases like 25 dB, it just performs quite well. I mean, they have you just have some magic parameters of 4 layers, and it performs quite close to BM3D. And until then, BM3D was like the golden standard. And then this paper just came, and they did some brute force, and they were able to show some comparable denoising performance. But what is the major problem with them? Is basically they just treated the whole patch as a fully connected layer. It's just as good as just jumbling the whole pixels and sending it in, because it's anyway fully connected. Every node is connected to the other. So it's so what were they missing was this they missed the whole spatial structure of the image. They didn't consider image as an image. They considered a set of values, and then they just did some denoising. So so one major one major thing that fully connected networks lack is this spatial structure. Like so which is brought in by convolutional neural networks. Basically, what they do is you have an input, and you have some set of weights, and each weight goes through. Basically, it applies a convolution. You can think of it like it just goes through all the neighborhoods, and then it creates a feature map, and then you have many of such weights. So you create the feature maps for each of them, and then they do some subsampling, and then they get some subsampling is basically just picking. They go to every 2x2 neighborhood, and they pick whichever is the maximum, or they take the average of this neighborhood, and then they put it in the smaller patch. So and so on. And this is for classification, but of course neglect the last few layers. So I want to just introduce this jargon called subsampling. And once you do convolution, then you apply a nonlinearity. Like previously, just you multiply it with a matrix. Just convolution is just some constrained matrix, block diagonal structure. So in deep learning jargon, this conv is called as a convolutional whatever. So ReLU is the activation function, which is basically non-linear soft thresholding. I mean, non-negative soft thresholding. We learned soft thresholding when we were doing ISTA. So it's just that, and then pooling is just pool is basically downsampling. You pool all the pixels, you take the maximum or the minimum, or the average. Yeah. So how is convolution? So basically, if I use your input and you're applying the moving thing is the weights. So basically, the green thing is the reconstructed output. So you can represent this whole thing as a block diagonal matrix. So if you can jam this blue vector into a single line, I mean single vector, then you basically are multiplying. When you're doing the first three multiplications, and then you have a 0, and so on, right? This is without zero padding. So in practice, this is actually neural networks convolutions are actually implemented as these sparse matrix multiplications. They just and which sparse matrix multiplications can be implemented really fast using GPUs. That's why GPUs are really useful when you're doing deep learning. So because everything that you have is basically matrix multiplications, mostly sparse because of the convolution. So it's and GPUs are really good at matrix multiplications. So that's why you have that's why they're implemented that way, right? And they don't do Fourier transform, by the way, because if you take your weights and if you do Fourier transform, it becomes a dense matrix. Then you have to multiply everything. So of course you prefer it to be sparse. At least that's what I think. Yeah. So let's say then there was another paper in 2016. That was the first appearance of neural networks in the scenario of deep learning, at least in the modern image processing. So they showed that you can just brute force every patch and just pass it through a fully connected network, and then output another patch, which will give you a denoised estimate, right? So here what they proposed was it was in 2016. They said that okay, you have the denoised, you have a noisy image, and then you do some convolutions. There's no pooling here. Notice that. So you take you take your whole image, and then you pick some big patch from it. Let's say 96 by 96 or something like that, and then you just apply these convolutions. And this transpose convolution is nothing but if you basically in how do you do convolution? You basically pad some inputs and then apply a convolution. Transpose convolution is where, let's say you want to increase from this let's say you want to increase from 128 by 128 to 256. So basically they just pad with zeros at every alternating column, and then they just do a convolution. So it kind of approximates. If all the weights are ones, then it's basically bilinear upsampling. So if, of course, they won't be ones, so it's kind of better than bilinear upsampling. But empirically, it's not that evident. So basically, what they propose to do was instead of learning from means they give input y, and you want to approximate x as the denoised estimate. So what they tried to do is they proposed to have a skip connection. What is called a skip connection? So basically, you send your input to the output, and you basically estimate the rest of it, the noise, using this network, using this fully convolutional network. The advantage of this is now, since in fully connected network we had like 2048 power 4 variables, if I'm right. Yeah, power 4 variables, and now we have much lesser, because you're applying shift invariant filters as convolutions, and then they basically propose to just approximate the residual. It's also a concept which is used in resonates, if you know, if you heard of it. Similar concepts were also successful in image classification. The main reason being, when you propagate the gradients from the output to the input, you have this problem called as vanishing gradients. So each gradient multiplies with the other, and by the time it reaches the input, it's almost zero. So to prevent this problem, you can just have a skip connection, which will just cheat and bypass the gradients to the forward layers. So you can just so you're essentially learning. You don't have this zero gradient problem. So two things. First thing, they proposed to learn the residual, and the second one is they had this skip connections, which basically gave them like having 0.5 dB is a really high benchmark in image denoising. Like previous papers just showed like very marginal improvements, and they showed that already the 10-layer network was able to beat PM3D and all the competitor algorithms. So it's really quite good, and these are the standard 14 images which people used to use for image processing to evaluate. It has Lena and all this stuff. So so they showed that this simple network, by just having such convolutions, 3x3 convolutions, stack them 30 layers, skip have a few skip connections symmetrically, and you're able to get best denoising performance than anything that existed by a huge margin, right? So also in other metrics like SSIM and stuff like that. So this is one application. Now let's talk about some other one. We'll talk about 3 or 4 applications, and then we'll go into perceptual loss, right? So another application is Lowdose CT Reconstruction. What is we saw how CT images are acquired, right? You have some X-ray source which is passed through your body, and then it reaches to the other side. And there's a detector which basically detects how much energy does this wave contain, the ray contain, and then you do it all across the body. So you basically have projections of all the directions in the body, and then you do a radon transform to get inverse radon transform to get back the image, right? So what is Lowdose CT is basically you just send less number of rays into your body. Like you send your rays with I mean, you make your rays follow a Poisson distribution. So you just hit less number of rays into your body. So basically, it's if you hit 4 times less, then it's 4 times less radiation. So lesser energy of X-rays entering the body, and then it decreases the ionizing radiation. So what these guys did was they just took a high dose CT dataset, and then they manufactured something like by using this Poisson distribution. They just kind of synthetically manufactured a Lowdose CT dataset, and then they just very simple thing. You can just ignore this for now. They wrote in the paper that this gave some marginal improvement, but even other than that, they just applied some fully convolutional network with several hidden layers, and they showed that this was able to perform really well. They minimized L2. Even in the previous case, it was L2 discrepancy that they minimized. So basically, you just have a low dose CT as input, and then high dose CT as the output, and then you're basically regressing from low dose to high dose. That's it. And basically, you can use the same network as it was used before. It's anything would work considerably well, and then you do some tweaking of parameters to get some more margins. Yeah. Yes. So it's not adding noise; it's Poisson, right? We saw that in Poisson, you basically shrink the distribution, and and then it converts into something else. It's not really adding, but yeah, in the previous case it was adding image denoising. With Poisson noise, it's not additive. It's yeah. So another example is fast MRI reconstruction. We also saw that in how aliasing artifacts occur in MRI. So basically, in MRI you acquire the k-space data. By k-space I mean the Fourier space data. Basically, acquire all the frequencies and phases at every point in the frequency domain, and then and most of the time is consumed because you have to acquire the whole frequency space. Even if you miss a few points, it will cost you a lot. So and one would like to acquire as less as possible, because each MRI scan takes like 25 minutes or something. If you acquire some less samples, then and still be able to reconstruct the same quality image, it's nice. So basically, what Facebook and NYU together, they were not the first ones who did it, but they are the ones who released like a ton of data set. Like I think 1500 volumes of MRI, which is open source. You can download in a click. So it's just, which is very rare in medical imaging community. So basically what they said was you just take a binary mask, something like this. Where is it? Okay, I don't have a mask. So basically you just, instead of acquiring the whole k-space, you just cut down a few parts, like you undersample the whole k-space by 4 times or 8 times. And then you'll be able, and then if you reconstruct it, you see this very blurry image with artifacts. So basically what they said was use the same thing, use the same architecture as you used before. I mean, this is a little different because they had some downsampling here, but eventually, I mean, yeah, everything works similarly. I mean, it's not really, you can get similar performance with this or the previous one. It's not that big a matter, but just you also have the skip connections, you have downsampling. Just downsampling makes it faster to run, that's it. Instead of, if you don't have downsampling, then you have a lot of feature maps, which will make it slower. So basically you can just get the undersampled MRI, put the fully sampled MRI, and then just regress the whole thing. And they use the L1 loss. And basically they used 1594 volumes for training. And they were able to reconstruct a high quality, by using undersampled k-space, they were able to reconstruct a good-looking MRI image. And the thing is that here, since they used only 25% of the k-space, basically you accelerated. I mean, it's not very true, but you kind of accelerate your acquisition process by 4 times. But they didn't validate it. They just collected the data set and then downsampled them. They didn't really use the sample, this binary mask, to acquire it and check, right? So that's one thing. So another one is deep ISP. So today we saw in the lecture what ISP is. So you have your scene, you have a lens, and then you acquire it using this Bayer mask in your camera, and then whatever happens later after that, and before you see your picture on the screen, whatever runs in between, it's called ISP. In mobile phones, usually we acquire with a very high frame rate, which means a very low exposure time. That's why most of the images that we acquire are actually noisy. The fact that we see good images on a mobile screen is basically we have very good ISPs implemented in our mobiles. For example, in Samsung. So this is one of my lab mates who did this. So basically, he captured some terminology. So basically, low lit images are basically which are acquired with a very short exposure time, and well lit images are the ones acquired with more exposure time. So for example, if you see this image, this is acquired with a larger acquisition time, and this one is with a shorter acquisition time. It's just green because it's the gamma wasn't correct. I mean, afterwards, what your ISP does is it takes this kind of image, it does denoising, demosaicing, and then color correction and gamma correction, and then it gets you the image that looks something like this. It's not really this, but yeah. So what he did was he just went and he created an app in which you can acquire both well-lit scenes and low-lit scenes very fast simultaneously. I mean, one after the other, not simultaneously. So since the acquisition speed is around like less than 10 milliseconds, so you almost get it, you almost have no motion in the scene. So, or shadows or anything that's moving, you won't have it. So kind of you have a static data set of both aligned well-lit scenes and the low light scenes. So basically what the traditional ISP does is it in the low level processing, they do denoising, demosaicing, and some gamma correction, color correction. Gamma is correcting the white. I mean, they basically say which. I mean, if you know some how you manufacture the camera, then you know which color leads to what. So if you do the correction, then you get then you get then you do some color correction. So what he proposed is he has a network in which the first n layers are doing some low level correction, which is just denoising and demosaicing, and then he gets a feature maps from he gets the feature maps from this layer, and then he kind of predicts the color matrix which you can add to your input and then do the color correction. So you can see the loss that he used is L1 error plus it's called multi-scale SSIM. SSIM is another measure in to calculate how good the image is, and multi-scale SSIM is just doing it at different levels and comparing the loss. It's fully differentiable. It can be implemented in TensorFlow and Torch. So, and then this is what he got. So this is the well-lit scene. Basically, if you had a camera which was open, whose shutter was open for a long enough time, you would have captured this. And this is what the camera actually acquires. And our mobile phones are mostly acquiring low light scenes because to maintain the frame rate. And then Samsung's ISP was able to reconstruct this, which was not as good. And this network was able to reconstruct a much better looking image than this one. And it's not only the best example, but he also did like a kind of survey on different images, and he also got this he hosted them on Amazon Mechanical Turk, and he got reviews from actual users. Because sometimes L1, L2 error and PSA and SSIM can't be really revealing of how good the image looks like. So he also found that just one network was able to perform much better than just what Samsung built for with thousands of engineers. So meanwhile, in classification, we saw that there is this very famous benchmark called ImageNet. So what they have there is they have 1 million images which are categorized into 1,000 categories. So until 2011, before the use of deep learning for this task, successful use of deep learning for this task, it was around 25%, and then there was a dramatic drop of around 8% or more than that, and then it kept, and then all these other things were by neural networks only. So so basically it's saying that neural networks are also good in doing classification. For example, this is some of the standard architectures. It's called AlexNet, which is which it was the same as what Jan LeCun, the inventor of ConNet, did 20 years ago, except that now you can run with much more examples and better GPUs, and you have a nonlinearity ReLU, which basically makes it successful. And then you have some other networks like this. It just has convolutions followed by ReLU, convolutions, and so on. This is called the VGGNet. I want to mention this because you can use this network really nicely in doing many tasks in image processing. So, for example, this is just some network which has several convolutions, ReLUs, and so on, stacked one over the other. And this is called VGG16 network because it has 16 convolution layers in it. And one nice thing that you can observe in neural networks is initial layers are capturing low level features, which means they're kind of reacting when they see edges or corners or things like that. And in mid-level features, you see some higher level structures. These are the feature maps. I mean, then when you pass the input and then you see what each feature map is looking at, is focusing at, or where it's getting more response at, you see that they're having some mid-level features, and the later layers are capturing more higher level features, or which yeah. So so here here we're going to talk about two different types of losses here. One is called I mean, we want to measure, we want to find some method in to quantify the style of the image. It's not really trivial. For example, using classical tools, it's almost impossible to standard image processing tools. How do you measure the style of an image? It's really not well defined. And the other one is feature reconstruction loss. First, we'll see what this means. So the key idea of this feature reconstruction loss, or sometimes it's also called as perceptual loss. So what it says is, these VGG features that we saw, they contain a lot of semantic information, which are usually they contain a lot of semantic information, and usually when we do this reconstruction task, we usually minimize for pixel wise loss, like we discussed. We saw L1, L2, MSS, multiscale SSIM, and or SSIM loss and things like that. But they might not really be indicative of something semantic over the image. They're just seeing pixels and they're just putting them accurately. So what they proposed is, instead of using those, you can optimize for the difference between these VGG features. They call it the perceptual loss, and basically you have an input Y, which is the degraded image. Let's say we're doing super resolution now. Y is a low resolution image, and X hat is a high resolution image, and you use the CNN to upscale the image. So you have ideally we would define something like this. We want to minimize the L1 norm between X and X hat, which will give us which is L1 or L2 loss, right? So instead, you can rather minimize this phi j of X. And what phi j means is, take a VGG network, fix the weights, which is pre-trained on ImageNet, and fix the weights, and then forward prop through the VGG the output that you get, and then minimize that difference, right? Fairly straightforward. And you take a pre-trained VGG network, you fix some layers, and then you match the outputs of your network outputs. You pass it through the VGG, and then you measure the loss. Yep. Yes. High level. Yeah. It depends on the task, actually. So you can usually high level. So you can see that as you go deeper, so your VGG level features are containing less structure and more semantics. It might not very evident here. So how they chose this which network to use is, they basically looked at which features are capturing most of it, and then they just minimize the discrepancy with respect to that. So instead of using pixel-wise loss, they just use this one. So Y is the low resolution image, and X hat is the network output, and X is the ground truth high resolution image. So, and then you minimize the VGG loss between them. So these are the results. So if you had minimized for SRCNN, is if you had minimized for L1 or L2 loss, just using CNN, you minimize using L1 or L2 loss, and that's what you get in SRCNN. And ours is the paper in which they propose they to use this just perceptual loss, use the VGG features. You see that SRCNN, for example, has a better SNR and better SSIM, but if you look at the images, this image looks more convincing, or looks better than perceptually than all these images. This is the ground truth. So this looks more closer to this ground truth than any other things, and it's also tested on Mechanical Turk, and many people voted for this. So what they say is, so sometimes SNR and PSNR and SSIM are not really good perceptual measures of how good an image looks like. And for example, in super resolution, we don't really, for example, you can't do this in medical imaging, right? You can't really invent stuff which is not there in inside your body. But if you don't care about if you don't really care about what you see, I mean the details of what you see, so this is a very good. Uh, I mean, this you can use such things and you can get good results perceptually. And then now our interest is basically we want to quantify what is a style in an image. So they define it the following way. Let's say you have you forward prop your image through AlexNet. Let's say you have this block which is your feature maps. C is the number of channels. H and W are the sizes of your output. So you take how perceptual loss is defined as I mean the style reconstruction loss is defined as. So you take every two channels. I mean every two pairs of H and W for different channels, and then you just calculate. You just tag this into C times H and W, and then you calculate the gram matrix of this whole thing. Basically, just if you have C times H times W, you just tag H and W into one vector, and then calculate this FF transpose F. Let's say this one. So you get some matrix which is channel by channel and not really depending on the number of what is the size of your H and W. So this what they claim is this particular matrix will capture the style of a particular layer in the network. For example, if you see this totally, since we just jumbled a H and W and stacked into a single layer, it doesn't really have any spatial structure in it. So if you so this is the visualization. This is, for example, one of the gram matrices in all these four. There is no spatial structure. It just captures how the style or so-called style looks like of this particular image. And then the loss is defined on if you want to convert one image from if you want to convert an image to a different style, then you can just define the loss on, you can just ask the reconstruction in some way that, okay, whatever you reconstruct, this gram matrix should be similar to this gram matrix, which means the style should be similar. So and then so which means if you have a network, let's say you have your input through this is your painting, and this is your random noise. You want to update your random noise in a way that it matches the style of it matches the style, as in this gram matrix is as similar as possible. Okay, so so now if you want to do a style transfer, let's say you have a content image and you want this content image to have the style of this painting, right? How it's fairly straightforward. We just use these both things that we discussed about. So we have a style target of how should the gram matrix of my output look like, and I have another content image which basically measures how my perceptual difference between the image that I produce and the actual input should look like. No, this is not yet the. Sorry. I just want the gram matrix from this style image, right? I take this image, I just forward prop through the VGG layers. I calculate this gram matrix, and then I have some target. Yeah. So you can choose different layers. So you don't have to pick one layer. They just they probably tried different things and probably they found this one works better. So that's how they choose it, and they define this L feet as basically the L feature loss, which is you pass it through a VGG and then minimize the difference between them. So eventually you want something like this, right? So I want a network which takes my input image, some random, let's say this is random noise, my input image. It will convert into some y hat, which minimizes the following loss. So it minimizes my y. It should be as close as possible to yc with respect to this perceptual loss, which we defined as the VGG loss here, and it has its gram matrix should be as similar as possible to the style target. Let's say this is my painting and this is my picture. So the gram matrix of this painting and the gram matrix of the output that I get should be as similar as possible, and then I want to have some some piecewise smoothness in the image I reconstruct, so I put some total variation loss, and that's it. So here is my style image, and this is my input, and you get fairly good looking images. So it has the style from this and content from this, and you're able to reconstruct really good images. I mean, this is some competitor method, and this is what they proposed, and similar things with uh, with other paintings. So it's really cool. So you have just what is a cool thing is you can just so recently Tomo Mikhaili from he had a recent paper saying that so if you optimize for this perceptual loss, it's kind of the opposite of optimizing for SNR. So you can't get both perception and distortion. Distortion means PSNR, and perception, and he actually showed in the paper, they kind of proved it, that they both are, if perception goes up, then the distortion will go down, and vice versa. So they showed that they took like 10 standard algorithms from the 10 recent papers, and then they showed that whenever the perception is high, the distortion is low, and they are basically inversely proportional to each other. So this so what would you ideally want to, if you want to have optimal amount of both perception and distortion, you just minimize both of them together. So you have pixel wise loss and the feature wise loss. So then that way you play both, you kind of fall into an equilibrium. So yeah, I think that's it. Last tutorial. Yeah, thanks. This one, right? Yeah, but the cool thing is you don't even know how to model these problems by using standard image processing techniques.